Hello everybody and welcome to today's lesson. We'll be doing some trig max and min examples starting with question 8. I'm Jake.
Hey Jake, thanks Jake. So a triangle has two sides A and B if the angle between the two sides is theta, or theta. So let's draw a picture. Okay, we got A, we got B, we got theta. And what do we know about theta? What must the angle theta be between? Between 0, well, why 90? Why can't it be obtuse? Obtuse is just greater than 90. It could be greater than 90.
It has to be less than 180.
It could be less than 180. Now, of course, we don't use degrees, right? So it's going to be between 0 and pi. We could say, it could be 0, I suppose. Well, you won't get much of a triangle there. But, so if theta were 0, you'd have no angle and therefore no area, right? So if theta equals 0, then A, the area would be 0. And same thing, if theta were equal to pi, the area would be 0. But remember, in a max-min problem, we have to look at the extremes, right? And any critical numbers. All right, what do we know about the area of a triangle? Yeah, so 1/2 base height. Okay, so we got our base, we need a height. So let's put down here, here's our height. But we're going to need our height in terms of the angle theta and the side A, okay, because we chopped the base here. We wouldn't know this length here, right? We just know this whole length, he says. Now we're going to record this. Can't just talk about and wave my hands. Okay, so in terms of A and H and theta, what's the relationship? Sine. So sine theta is what? H over A, right? So we need H though, right? So what's H? Okay, so H is A sine theta. Okay, because we've got this formula, and now we're going to have two variables there, right? All right, so what's H? Oh, well, so if we can get the highest height, considering the base is a constant, the highest height will give us the maximum area, right? So all we have to do is maximize the height. Okay, make sense? We maximize the height because the base is constant. If we maximize the height, then we will get a maximum area. We maximize the area. All right, and we have an expression for height. H equals A sine theta. We are going to take the derivative of both sides with respect to theta. So dH by d theta is equal to what? What's A cos theta? A cos theta. Now, is it easy to take the second derivative?
No.
Seriously?
Wait,
A cos theta? Hey, if you want to do the first derivative test, that's okay, but I just assume. Remember the second derivative test? This is where it comes in handy, right, on max min. If it's easy to get the second derivative, then we can see if we have a max or a min. Hopefully, it'll be a max. All right, so what's d2h by d... What's second derivative? Negative A sine theta. Now, in our domain of 0 to pi, what do we know about sine theta? It's always positive, which means negative A sine theta is always negative. So the second derivative is negative. Second derivative is negative means that it's concave down, which means we have a max. Okay. So any max-min problem, you have to show that it is a max or it is a min. Okay? You can't leave that off. How can we do that? In this case, if it's easy, find the second derivative and evaluate it. Okay, now in this case, anywhere in the domain, sine theta is positive, so it's always negative. We don't have to actually evaluate this at a particular value. Okay, now, what do we want to do? Well, okay, we want to maximize this, right? So we have to do what? Find the critical numbers, right? So we will get a max. We will get a max when a cos theta is equal to 0. Okay, now being as a is never 0, that means that cos theta has to be 0. So cos theta equals 0, and when is cos theta equal to 0? So pi over 2, also 3 pi over 2, but that's outside of our domain. So we're just sort of being, just in case it were in the domain, we don't want to forget that. But in this case, we cross that off. So we say we have a max at pi over 2, and what did it actually ask for? Determine the value of theta. Okay, so we've done it. Right? Y is the max. Okay. So the angle that maximizes the area of the triangle is pi over 2, right? Not always. Okay, determine the maximum perimeter of a right triangle with hypotenuse 20 centimeters.
No, we didn't.
I don't have notes on it.
You want to see it? Okay, we'll go with you haven't done it yet. Apparently. I don't know. Did you get? Well, have you guys done it? It's like what it's. All right, I'll do it. Then you still won't understand it. You'll just put it down to this question cannot be understood. Doesn't matter, man. 2 people tried. I'll try. We'll see. All right. So to max perimeter of a right triangle. So we don't really know anything about the other sides except that this squared plus this squared is equal to that. But so I guess you could do it. I mean, if you define this, no, you can't really, right? No, we don't know. So we're off to a good start. So let's just pick an angle here, right? So in relation to the angle, what's this side? What's the length of this side? All right, I'm going to give that a name. So, if that's a, then sine theta is a over 20. So a is 20 sine theta, right? So this side here is 20 sine theta. Right? Everybody's done physics, you know this stuff, right? Because you're always working with the force diagrams down an angle, right? So what's this side here? 20 cos theta. So the perimeter is 20 plus 20 sine theta plus 20 cos theta. All right, so, and what's theta? Between, actually pi over 2, right? So it's the right triangle. Now it can't be 0 and it can't be pi over 2. Those are the extremes though. So we may need to look and say, when theta is 0, what do we get? When theta is pi over 2, what do we get? And then when it's whatever angle we find, which is probably pi over 4, but that's just the way these things work. What do we get? Okay, so P prime. What do we get there? 20 cos theta minus 20 sine theta. Okay, so, can we do P double prime? Say yes. Yeah. So P double prime will be minus 20 sine theta minus 20 cos theta. And in our domain, what can we say about this? Negative, concave down, max. Okay? So any max min problem, you have to justify whether it's a max or a min, right? You can't just, I solved it, there it's not. No, you got to show. Okay. So if you could do second derivative test, very handy, right? If not, first derivative, table, chart, arrows, max min. All right, what do we want? We want P prime equal to 0. find the critical numbers. So that gives us 20 cos theta minus 20 sine theta, which tells us what? Divide by 20. So that says cos theta has to be equal to sine theta. Actually, let's write that as sine theta equals cos theta. So you can either go, oh, I know when that happens, right? Or you could say tan theta equals 1. So divide both sides by cos theta. And then you could say, oh, I know when that happens, which is when the other thing happens, which is when theta is pi over 4. So theta is pi over 4. So now we need to examine the perimeter at 0, pi over 2, and pi over 4, right? Because maybe it's a max. Obviously, it's not a max at 0, nor is it at pi over 2, right? Because you just can't make triangles. But we still have to. So p of 0 will be 20 plus 20 sine 0 plus 20 cos 0, which will be 40, right? That's 20, that's 0. And that's a 1, so that's 20 plus 20 gives me 40. And same thing's going to happen at pi over 2, only it'll be the 20 sine theta, so 20 sine pi over 2, 20 cos pi over 2. So that's 20. This is a 1. That's a 0. So 20 plus 20 is 40. Right. It just basically means you created a flat triangle and just got a side of 20 lying on top of a side of 20, or very, very close to it. Right? You got the hypotenuse is 20. You've got a minuscule height, minimum height you could get, 0.0001. The other side is going to be just slightly smaller than 20. And p of pi over 4, which is 20 plus 20 sine pi over 4 plus 20 cos pi over 4. There's 20 plus 20 root 2 over 2 plus 20 root 2 over 2, 1, 10, 1, 2. So it's 20 plus 20 root 2, which is greater than 40 and is the max. Right? Because these guys are both 40. That's, root 2 is 1.4. So that's bigger than 20, that's bigger than 40, and we have a maximum. Okay? Make any more sense than it did before? Oh, yes. Yeah. How was any different?
Because he did this weird number line stuff.
Put everything on number.
Yeah, he did these weird number lines.
Oh,
Like, please
okay.
stop it. Just go. I'll just do it in the video. You should have just put the video on. Next time you're stuck, you just tell me to put the video on.
I could. Except this video needs a correction. That's why it's being re-recorded. Determine the dimensions of the rectangle of maximum area that could be inscribed in a circle of radius A. Who would say A for a radius, right? R. Radius R, yes.
Did we finish artificially solve the last question? Yeah. Ask for the maximum.
Yeah, it's 20 plus 20 root 2.
Is it?
Yeah.
Okay.
Because it's bigger than 40, so that's the math. I don't know, is it in centimeters or something? Were there units? Oh, hang on. Units. Yeah, so we'll really clean this up. Centimeters, which is greater than, so 20 plus 20 root 2 centimeters. We didn't enumerate it, right? It's like 1.4, or 20 is like 8, it's like 48-ish. Okay, draw a picture. So what do we got? A rectangle. What do you think this rectangle is? It's a square. Yeah, the rectangle largest area is always a square, right? But whatever, we still have to do this. Okay, so we got this. So what measurements do rectangle? They got lengths and they got widths. And what's this distance here to here? But it's also what? 2r. 2r. Okay, so we know, what do we know? Area is length times width. And we have the relationship that L squared plus W squared is equal to R squared. Okay. So we want to get stuff into, now R is just a constant, right? So like if this thing said determine the rectangle max area could be described in a circle of radius 5 centimeters, right? So the R is some constant, right? It's W and L that are going to vary here, right? We're looking for the W and L, the width and the length, that in relation to this constant value give us a maximum area. Okay? So it's more of a general, and that's not R squared, that's 2R squared. Okay, so here's what we're going to do. We're going to solve this for W, then we'll just work area in terms of length, okay, and then do the derivative. So L squared plus W squared is 4R squared. Okay, remember, R is a constant, so don't worry, there's an R. W squared is 4R squared minus L squared, and so W is the square root of 4R squared minus L squared, right? It's the principal or positive square root, okay, because normally if you're solving for W squared, blah, but this is a length, so therefore it's positive. Okay, so now we go back up here and we say, so it's length times width, and the width is, now let's write that to the half. All right, so we need A prime. So we need the derivative, right? And we got a product. And remember, 4R squared is a constant. Okay, so its derivative is 0. Okay, so what is it? First times the derivative of the second. So 1/2, so L times a half of 4R squared minus L squared to the negative. You didn't leave enough room for yourself. Okay, so A prime is equal to, so L times 1/2 4R squared minus L squared to the negative a half times, okay, this is 0, minus 2L. Okay, so we got a half and an L and minus 2L is just going to be a negative L squared. Right? So the half is going to take out 2. And, okay, but we got to keep going. Plus 4R squared minus L squared to the half times the derivative of L, which is 1. Yeah. You don't need to put the 1. So if we take out a common denominator, what will it be? 4R squared minus L squared to negative 1/2. R squared. All right, and what do we got here? So we've got a negative L squared. And over here we've got a plus 4R squared minus L squared. Okay. So, maybe that wasn't the best thing to do. In retrospect. That's why you use pencil. So in retrospect, what do we got? So we got a 4R squared minus, so we've got the root of 4R squared minus L squared, and then we'll pull this over, minus L squared over the root of 4R squared minus L squared. Okay, yeah, so this will work out better. What do we know about L and W? So that L is somewhere between 0 and 2R, right? And W is somewhere between 0 and 2R. right? Just set our boundaries on here. So in other words, if it was just along here, my rectangle, that would be 2r for the length. But then the width would be 0. So if L was 2r, the width would be 0. You'd end up with an area of 0. If W was 2r, you'd end up with a length of 0. So that's our boundaries, right? Because remember, we have to do boundaries. Okay, so we want to set A prime equal to 0, right? So we set A prime to 0. Do you want to do the second derivative? No, this time we do not want to do the second derivative, right? It's not easy. So we set A prime equal to 0 to find critical numbers, which means we are going to have to do a chart, right? We'll have to do a chart to look at the first derivative and find out if we have a max or a min, right? Because we want a maximum area. Okay, so if this is 0, so 0 is equal to the square root of 4r squared minus L squared. So let's kick this over to the left-hand side, where it'll become positive. Square root 4r squared minus L squared. And it'll be equal to the square root of 4r squared minus L squared over 1. And so we could cross multiply. So L squared will be equal to, so cross multiply is just going to get rid of the 4r squared minus L squared. Get rid of the square root sign. So 2L squared. 2L squared is equal to 4R squared. Okay. And again, remember, we're solving this in general, right? You could, once we solve this, you can give any radius, right? And then just plug that in and figure out what the length and the width are with respect. So L squared will be 2R squared. So L is root 2R squared, which is root 2R. All right, so we now know that the length is the square root of 2 times the radius. Okay, whatever the radius is, right? Radius can be any number. And being as it can be any number, we'll go up and we'll do our little chart. Okay, so we know we got a 0, we've got this root 2r, and we've got 2r. Okay, so the length is between 0 and 2r, and the critical number is root 2r. And what we're going to look at is, what's the sign of A prime? Okay, so what's less than root 2r that we could put in? And you could say, well, you could just use r. So if we're in here, if we take r and throw that into A prime, which is up there now. So if we just throw an r in, this will be the square root of 3r squared minus, this will be r squared over the square root of 3r squared. So this will be bigger than this, right? So it'll be positive. And if we take something close to 2r, this is going to be like 0, right? Because you'll have 4r squared minus 4r squared, and that'll be 0. And it's not quite 0, right? But this will end up being very small, and this will end up being negative infinity, because you'll be dividing by a number close to 0. So that'll be minus, so this says this goes up, and this goes down, leading us to what type of shape? So what have we got? Got a maximum, right? Okay, so max. This is a max. Okay, so using the first derivative test, we have shown that we are going to have a maximum. Yeah, well, I tried an r here. Oh, here? No, I just went close to 2r. So if we go as close to 2r as we can, this could be really close to 0. So is this, which makes this really small. This is just going to be minus 4r squared over small, which is going to be negative infinity. Oh, sorry, it's going to be infinity, and then when you subtract it, it'll be negative infinity. All right, so now what? We need the width. So what's the width? So W is the square root of 4r squared minus L squared. So W is equal to the square root of 4r squared minus L squared. and L is root 2r. So 4r squared minus root 2r quantity squared. So it's the root of 4r squared minus 2r squared. The root of 2r squared is root 2r, leading us to the shocking discovery that this rectangle is really a square. Okay, what are we supposed to find? Determine the dimensions. Okay, so the dimensions of the, drop this, the dimensions of the rectangle of maximum area are root 2r by root 2r. At which point we could say that's a square. Okay, any questions? So is it because other people laugh when you hit it that makes it funny? Now I know what you're thinking, right? And you're not really thinking it, but I'll tell you what you should be thinking. You're thinking, wait a sec, we just got into doing this stuff with trig, and here you are solving this geometrically, right? Can you do this using trig? And I say, well, let's give it a try. So we'll skip ahead. It doesn't matter because you're just working on your piece of paper there. So, number 10, using trig. Okay, so it turns out that a lot of things that could be solved geometrically may also be able to be solved using trig. All right, so we've got our circle. We've got our rectangle. All right, we know this is 2r. We know this is L, we know this is W, and we say, hey, there's some angle in here, theta. Right? And you want to find the value of theta that will maximize the area of the triangle. Okay, so we go back here and we say, well, area is length times width. And we go over here and we say, but sine theta is equal to W over 2r. So W is equal to 2r sine theta. Remember, r is a constant. So 2r is like having the number 20 there, right, or something else. And cos theta is equal to L over 2r. So that L is equal to 2r cos theta. Okay, so here's what we've done, right? We have expressed both W and L in terms of r. And theta, because r is a constant, so it's really just the theta that we're interested in, right? So we go back over here and we say, okay, so the length is 2r cos theta, and the width is 2r sine theta, so that A is equal to 4r squared cos theta sine theta. And you say, but what's cos theta sine theta? Well, what? Yeah, so, hey, what if we borrow a 2? We're not going to borrow a 2. What if we take a 2 out of the 4 and call this 2 sine theta cos theta? And we could say, hey, that's just the sine of 2 theta, right? And it's not that you can't do the derivative of this. It's just, why not simplify it? So this is 2r squared times sine 2 theta. Okay, and that's easier to do the derivative of, right? Okay, remember, 2r squared is a constant. So when we do the derivative, it's just going to be 2r squared. Okay, It's a constant. And then we do the derivative of this. So 2r squared. And then here the 2 comes out, right? And it's going to be 2 cos 2 theta. So we're going to get 4r squared cos 2 theta. Okay, so there's A prime. Makes sense? We're going to kick up over here. So we want A prime to be 0. Well, I guess we could do the second derivative, right? Yeah, that's not hard to do. Okay, so let's move over here. So A double prime will be, okay, so the 4r squared is a constant. Yeah, we got that. The 2 is going to come out, right? So it's going to be 8r squared. Oh, wait, but it's going to be negative. So negative 8r squared sine 2 theta. At which point we got to say something about theta. So what's theta going to be? Well, 0 is less than or equal to theta, which is less than or equal to, okay? So it can only go up to pi over 2, right? Because it can only go as high as here. It can't open up flat. You can't have an obtuse triangle in there. Okay, so in our range from 0 to pi over 2, sine 2 theta means that 2 theta is going to go from 0 to pi. The sine of 0 to pi is always positive, so this is always negative, so it's concave down and a max. Okay, so in our domain, sine 2 theta is greater than or equal to 0. So A double prime is negative, which is concave down, giving us a max. Ah, see, now we didn't have to do the first derivative test on the other one. All right, now over here, we want A prime equal to 0. Find the critical number. So 4r squared cos 2 theta is equal to 0. 4r squared is a constant, right? So just divide both sides by 4r squared. So cos 2 theta equals 0. So, what's theta? Well, it's the cosine of pi over 2 is 0, right? So that means if I throw a pi over 4 in for theta, then, so it's going to be pi over 4. Okay? Is that okay? Everybody's okay with that, right? Because cosine of pi over 2, so 2 theta has to be pi over 2, so theta is pi over 4. Right? So I'll just say, so 2 theta is equal to pi over 2, and theta is pi over 4. The next one is 3 pi over 2, so that would be 3 pi, okay, so don't worry about that. Or 3 pi over 4, that's outside the domain. Therefore, the angle is pi over 4. Okay, so the angle, so we have a maximum area when theta is equal to pi over 4. Okay. But it didn't say what's the angle, right? It said what are the dimensions. So W is equal to 2r sine pi over 4, which is 2r root 2 over 2, which is root 2r. And L is equal to 2r cos pi over 4, which is equal to root 2r. W. L, the dimensions, ... Okay, same conclusion we drew with the other way. So dimensions are. Advantage, disadvantage. I don't know, advantage, we didn't have to work out didn't have to do a first derivative test on the thing. We don't have square roots hanging around, right? So the derivatives were easier to do, both first and second, giving us the fact that it was a max. But just shows you could do it either way. Okay? Two more. Oh wait, I gotta go back. 2 more. Determine the angle theta. So in this case, we do want the angle that maximizes the area. Anybody know the formula for the area of a trapezoid? Well, it'll be given to you if you need it.
Is it 1/2 A plus B times H?
It is. So let's call this A. So the formula is 1/2 A plus B times H, where A and B are the parallel sides. So a trapezoid has one pair of parallel sides. Okay, so then B is this length. H is the height, or over here. Okay, so in terms of theta and 5, what's H? Okay, what can our angle theta be between?
909 or power 2.
Actually, you can go from 0 to pi, right? So, I mean, the theta could be there. But, I mean, if it's 0, the area is 0. If it's pi, the area is 0. Right? So here's theta, the angle is 0, and here's theta, the angle is pi. Okay. So that side could be folded flat, but if it is, there's no area. But theta is between 0 and pi. And, okay, what do we got here? So theta, we got opposite hypotenuse. So sine theta is equal to h over 5. So h is 5 sine theta. Okay, what's b? Well, b is a in here plus, what's this length here then? So this is 5 cos theta. So b is going to be a plus 10 cos theta. Okay, so there's a, which is there, plus, or this b is this length here. So 5 cos theta plus 5 cos theta. All right, so a is 1/2 a plus b plus a plus 10 cos theta times h, which is 5 sine theta. Oh, but what's a? A is 5. Duh. Okay. Clean that up. 5 plus 5. Okay. Yeah. So a, that's 5. Okay. A is 5. That means this is a 5 up here. Okay, and h, so we only have one variable now, right, which is the theta, which we're going to maximize. Okay, so what do we get here? 10 plus 10 cos theta, so 1/2 of that. So we do 5 plus 5 cos theta. Okay. So let's take this here. So it'd be 5/2 sine theta times 10 plus 10 cos theta. Okay, so we got the 1/2 and the 5 sine theta. We're just going to move this up front. It becomes 5/2 sine theta. And then this 10 plus 10 cos theta. Okay, don't want to do this as a product because we can just multiply the sine theta through, right? So a is equal to, so 5/2, 10, this will be 25 sine theta plus 10, that'll be a 2, so it'll be 25 sine theta cos theta. Hey, wait a sec. We just did one where we had a sine theta cos theta, right? What are we going to do with sine theta cos theta? We're going to change it into sine 2 theta, right? But we don't have a 2 in here, right? Unless we make this 1/2 of what it was. So 25 over 2, and then we can go sine 2 theta. So we got 25 sine theta. We're going to borrow a 2 from here, right? Now we're going to factor a 2 out, so it becomes 25 halves. Okay, so this now becomes, so this becomes 25 halves and 2 sine theta cos theta. Okay, so we're just doing that on our scratch pad and saying, so I got the 25 halves, and this guy here, that's sine 2 theta. Sine 2 theta. Okay. Whose turn is it to derive? I think you can derive that. Not only can you derive that, you can second derive that. Yeah, well, that's an A prime. So what do we got? We got 25 cos theta. Plus the 2 is going to kick out, so it'll be a 25. Cos 2 theta. Right, which is 25 cos 3 theta in your dreams. It's not 25 cos 3 theta. You can't do that. Don't do that. You can't do that. Yeah, I have it somewhere.
It's so lost in the phone.
All right, let's do a double prime while we're here, because it's pretty easy to do, right? So we're going to get minus 25 sine theta minus 50 sine 2 theta. And did we say anything about theta? Oh, we did, yeah. It says between 0 and pi. Good. So if, yeah. So that's going to be negative. Concave down. Max. All right, so we have a maxima. Well, no, do we? No, we don't actually know, right? Because the problem is this: if 2 theta, if theta is between 0 and 180, this could go into the negative values for sine theta, and then you got a negative, negative. Okay, so we're actually going to have to find the particular angle and then evaluate the second derivative at that angle. Okay, so we don't know now because 2 theta could take us into angles between, because that's pi, could take us angles between 0 and 2 pi, in which case the sine thetas could be negative, and then this negative, negative could be positive, could override that. Actually would override that likely, but whatever. Okay, so A prime, critical numbers. A prime equals 0. So 25 cos theta plus, where did you stop writing? Plus 25 cos 2 theta is equal to 0. All right, what are we going to do with cos 2 theta? Turn into 2 cos squared theta minus 1, right? Which will then give us a quadratic in cosine theta. So we're going to turn cos 2 theta. So 25 cos theta plus 25. We'll turn this into 2 cos squared theta minus 1. Fine. Okay, so cos theta plus. Okay, so dividing both sides by 25 and replacing cos 2 theta with 2 cos squared theta minus 1. We now have a quadratic in cos theta, so 2 cos squared theta plus cos theta minus 1 equals 0. Okay, factor. 2 cos theta, cos theta. I need a plus 1 minus 1, because we're at plus 2 minus 3. Yeah, okay. So either cos theta is 1/2 or cos theta is negative 1. Okay, so cos theta being negative 1 happens where pi, right? So theta equals pi. And cos theta is 1/2 happens where between 0 and pi, right? So it's just going to be in quadrant 1, pi over 3, right? Yeah, pi over 3. Okay, now we know that when theta is equal to pi, right? Because since the area will be equal to 0. So we can reject the pi, right? If theta is lying flat out, you don't have a trapezoid, you got a line, no area. So now we got to go up here. We have to evaluate a double prime at pi over 3. So negative 25 sine pi over 3 minus 50 sine 2 pi over 3. That's negative, right? Sine pi over 3 and sine 2 pi over 3 are both positive. Okay? So I'm not going to work it out. It's negative. Therefore, it's concave down. And therefore, it's a max. Because sine 2 pi over 3 is positive. So I have negative 25 times the positive minus 50 times the positive. That's negative. Okay. You could work it out if you really wanted to, but yeah. Okay, so the trapezoid's maximum area occurs. The trapezoid's maximum area occurs. Okay, I can never spell occurs. How many C's, how many R's? 2 C's, 1 R? Ships sail to 7 C's. That's where it occurs when theta is equal to pi over 3. Okay, so remember, it's not enough just to solve this. You also have to show that it is a max or it is a min. Okay? Right. Don't worry, we've got plenty of time. We got one example to do. Okay, ready? Last one? Questions? You gotta go. We'll have a brand new video to watch. And actually, it's the next example that is the reason why it's a brand new video. But we'll start this off. You just go when you gotta go. All right. Is it like a rugby game or something?
Yeah.
Okay. So, one hole. What do you got to leave? Why don't you just go now here? I'll just pause this. Y'all can go. The famous ladder/pipe problem, which is you're going to walk down, you got a right angle hallway in a corner, and you got to figure out what's the longest ladder that we can get around this hallway, right? Or the longest pipe, if you're carrying a length of pipe and you got to get it around. What's the longest piece of pipe, whatever. So let's draw a diagram to show you what this looks like. So here's the hallway. And this hallway here is 8 feet wide. And this hallway here is 4 feet wide. And you're going to carry a ladder. So if you think about it, if I had an 8-foot ladder, I could just fit it across the hallway like this, walk up here, and then just walk it down here, right? Wouldn't be a problem. If I had a 4-foot ladder, I could do that, and then I could actually turn it, right, and walk it. But I have to be able to get this ladder around a corner, so here's the problem. What's the longest ladder that will actually make the corner, right? So that when I get the ladder, right, because I'm walking the ladder straight, and then we turn it, it's like getting a sofa through the same deal, right? Anybody who's moved any furniture knows this problem. Okay, so we got to be able to turn it, we can get it on an angle, so I could turn it such that when its length is here, it can flatten out, right, and go around. Okay, so we need the longest ladder. So here's how we're going to do this. Let's say, well, there's an angle theta here, and this is 4. And because of similar triangles, if that's theta, these lines are parallel, this is the transversal, then this angle is also theta down here. Okay, and we have the length of the ladder, which is L. But we're going to split it up into 2 portions, A and B. And So what kind of angle can I approach this at, right? So 0 degrees, right? If you had a 0 degree angle, ladder would come along here. So 0 and then 90 degrees, right? So theta can be anywhere. And it actually can be 0 degrees here, right? Because it's not really a triangle we're worried about. It's the angle. So it could be 0, could be 90. If it's 0 degrees, then the length of your ladder is going to be 8 feet, right? Because I can walk along here with the ladder, have an 8-foot ladder, and then I can make it around here. And if it's 90 degrees, then it's like this, then it has to be 4 feet, because that's the only way I can walk it along here. Okay, so we're somewhere, likely theta is going to be somewhere between 0 and pi over 2. All right, so let's start off the way we have started so many of these. Okay, I got 8 feet, I got theta, I got A, and the relationship is, so it's going to be like cos theta, right? Cos theta is equal to adjacent 8 over A. I want to solve this for A. So A is equal to 8 over cos theta. And I do not want to have quotients in here when I start taking derivatives. So this is what? 8 secant theta, right? A cos theta, which leads to A is equal to 8 secant theta. Oh, you're done? Good. Yeah, take home. Okay, and B. What are we going to do for B? So we're going to do sine theta. So sine theta is opposite over hypotenuse, which is 4 over B. So B is equal to 4 over sine theta. And again, we don't want that, so what do we got? 4 cosecant theta. Okay, so we know the length is A plus B. Which means the length is A, 8 secant theta, plus 4 cosecant theta. And we want to maximize the length, right? So we do what? Take the derivative, L prime. Now, thankfully, we have a formula sheet, right? Because nobody remembers that the derivative of secant is secant tangent. So 8 sec theta tan theta plus 4, oh, not plus though, right? Because the derivative of cosecant is minus cosecant cotangent. So this will be minus 4 cosecant theta cotangent theta. Okay, at which point we say, I am not doing the second derivative because it's products. Okay, so not worth doing the second derivative, right? Better to just come up with an answer and then throw it in the thing and find out that we have the longest ladder. All right, so we got to set L prime to 0, right? So critical numbers, numbers, L prime 0. Okay, so 8 sec theta tan theta minus 4 cosec theta cotan theta is equal to 0. Okay, what might you want to do first? You could take out a 4, right? Yeah. So this will be 2 secant theta tan theta minus cosecant theta cotan theta is equal to 0. Here's where the magic happens, right? So we got to do something to magically, you can't solve that, right? Not the way it is. So you say, if I were to multiply through both sides, everything, by sine theta tan theta, right? So I'm going to tell you what we're going to do, and you're going to go, how did you arbitrarily choose that, right? And it's not arbitrary, because we're going to see what happens. So multiply both sides. Oh, well, hang on. Before we do that, here, let's do this. So 2 secant theta tan theta is equal to cosecant theta cotan theta. Okay, if it makes more sense, you're going to say multiply both sides. Okay. Wouldn't have mattered, though. So multiply both sides. By sine theta tan theta. Now you're saying, why would you do that? Right? Why would you choose sine theta tan theta? So, what is cosecant? 1 over sine. So if I multiply this by sine, this becomes 1. What is cotangent? It's 1 over tan. So if I multiply this by tan, it becomes 1. So when I multiply both sides by sine tan, this becomes 1. Okay, right? You got rid of a whole expression. Now we just got to figure out what happens over here. So 2. Okay, secant is what? 1 over cos, right? So we're going to say, okay, look, I'm going to multiply by sine. Okay, that's over cos theta times tan theta times tan theta. Right? So, secant, okay, I'm multiplying by sine tan. So this is the sine. I'm just writing secant as 1 over cos. Okay? So this is sine, secant times sine is this, times tan theta, and then I'm multiplying by sine theta tan theta, so we get another tan theta. And this side, we figured out it's just 1. Okay, what's sine over cos? Tan. So we have 2 tan cubed theta is 1, which means tan cubed theta is 1/2, and tan theta is the cube root of 1/2. So that's an actual number, right? Cube root of 1/2 is an actual number. That's what tan theta is. Now, are we looking for theta? Did it say determine the angle? No, it says determine the length of the longest ladder, right? Okay, so we have solved for tan theta. So now we got to show that it's a maximum, right? So what was our first derivative, right? So first derivative is sitting here, L prime, 8 secant theta. Okay, so we're going to make a chart. It's going to go 0. It's going to go, our angle theta, whatever it is, right? We don't exactly know what it is, but, and we got pi over 2 here. And this is just going to be a kind of, I'm just going to write what is L prime, right? So we'll just figure out what is L prime. So all we got to do is go really close to 0. Okay. So if I'm very close to 0, what is 8 secant theta tan theta? So we know the tan of 0 is 0, right? Yep. Okay. So secant theta, it's going to be 1 over really close to 1, but this is a 0. So this is really going to be very small. Okay, cosecant of 0. So cosecant is 1 over sine. Okay, so it's going to be 1 over 0, which is pretty big, right? And remember, it's not 0. And cotan is 1 over tan, which is going to be really big. So we've got minus 4, really big, really big. So we got 0 minus 4, really big, which is just going to be negative, right? Okay, so that's negative. And now, we know theta is somewhere between 0 and 4, so let's just go really close to pi over 2. So pi over 2, the tangent is positive infinity, right? At pi over 2, cosine is 0, but we've got 1 over cos. So we got 8 times infinity, minus 4 times, and the sign there is going to be, pi over 2 is going to be 1, close to 1, and the cotan of pi over 2 is going to be like 0, right? So it's going to be 8 times infinity minus, so it's going to be positive. Which means this is down, this is up, and we have a, not a maximum. Not a maximum. We have a minimum. But here's why it's a minimum. Okay? So the longest ladder that you can get around the corner is the shortest distance between these 2 points. Right? The longest ladder, so we really are working out a minimum here, right? But what the minimum working out is, what's the shortest, let's call that P and call this Q. What's the shortest distance between P and Q such that I can actually get something through there, right? And the longest ladder is the shortest distance between these 2 points, right? If it's any longer than that, it won't fit, right? It bumps the wall. Okay, you need to be able to kind of fit that across and then pivot it. Okay, so once we got this running across here, and it's just touching the walls or not touching the walls, then we can pivot. So it's really a minimum problem. Who knew? Right, the longest ladder is the shortest ladder that will actually fit between those 2 points. Okay. Now that we know we're looking for a minimum, now we can actually just kind of work it out. Okay, so what is that length? So we just go back to our diagram, so you can just look at the diagram you have. So we know that tan theta is equal to 1 over the cube root of 1/2, or, sorry, 1/2 should be 2. 2. Yeah, why don't I have a 2 here? 2, tan cube theta. Oh. Okay, well, okay, we could write it. We could go 1 over the cube root of 2, right? Okay. Could do that. Same thing, right? Cube root of 1/2 is, because cube root of 1 is 1. Okay, so tan theta is 1 over cube root of 2, or the cube root of 1/2. Doesn't really matter. But tan theta is defined as y over x. Okay, so here, what we will say is that means that y is equal to 1, and x is equal to the cube root of 2. And then we can work out r, right? Once we got x, y, and r, okay, because what do we need? I mean, where are we going with this? We're going to go back here, right? The length is 8 secant theta plus 4 cosecant theta. So we need x, y, and r so we can get secant theta and cosecant theta. We don't need theta. Who cares? Doesn't matter what the angle is. What matters is that we have secant and cosecant. But in order to get those, we need x, y, and r. Okay? So we had tan theta, we have y and x. So r is equal to the square root of x squared plus y squared, which is the square root of the cube root of 2 squared plus 1 squared. So it's the cube root of 2 to the 2/3 plus 1. Okay, that's r. So we got x, we got y, we got r. We know that L is 8 secant theta plus 4 cosecant theta. Okay, secant. So cosine is x over r, so secant is r over x. So it's the square root of 2 to the 2/3 plus 1 over x, which is the cube root of 2, plus 4 cosecant theta. So cosecant, so sine theta is y over r. This will be r over y, plus 4 cube root of 2 to the 2/3 plus 1 over 1. Page. We can factor out a 4 times the square root of 2 to the 2/3 plus 1, giving us a 2 over the cube root of 2 plus 1. Which is about 16.6477 feet, so call it 16.64 feet. Okay, now anything similar to this on a quiz would give you better numbers, right? Because it's not like, and I had to spend 20 minutes cranking through this stupid cube root of the, whatever. So, no, because then it'd be too long. It's going to bump and somebody's got to be patching drywall.
How many of these long questions?
That's the whole test is just this stuff. Just ladders. It's called scaffolding. When we learn stuff and build upon it, it's called scaffolding.
Yeah,
So we're just gonna,
Is there really possible that two of these long questions?
Oh, long question. This is a long question. How long did this take? It's like 41, 20 minutes. Yeah. No, there will be a likely easier one of these, right? But a matter of setting it up. Now, keep in mind, you can do this question. If you don't do the angle, you can still do right triangle trig and Pythagorean theorem. So you can solve this geometrically as well. And I know you would love to do that, but we don't have enough time. So, yeah. So, are you sure we can't do that? I don't know. What is tomorrow? Okay, so then we're done, right?